Hi, I'm Paul Battaglia, and this is section 11.5. One of the things that I like to do, and this is a personal preference, is I like to impress upon students the idea that the formulas presented for summations at the beginning of this section are really not crucial to their understanding of the concept of the area problem. So again, a personal choice. I may go through a couple examples with my class, but I'm really more focused on getting them to understand what the area problem is all about, how it ties into calculus and limits. And so I'm joined by Gabe and Brittany, and what they're going to do is walk you through how they might structure their lesson for their students. Brittany, let's start with you. What is it exactly that you want students to take away from the area problem, or even just to get them started?
All right, to start the discussion of the area problem, I will just draw a curve up on the board and ask my students, well, what's the area underneath this curve? Well, it's a shape that they don't have a formula for. And so I say, well, is there any shapes we can use? And they might just, start shouting out things that they know. So maybe they'll say triangle, circle.
Yeah, anything from geometry I remember,
Yeah, and so hopefully that we'll hear a student say, how about a rectangle? And I'll say, yeah, let's try a rectangle. And then I'll lead into more of a
discussion. Okay, I think that's good. And I think, Gabe, if we make that commitment to use a rectangle, because it certainly doesn't have to be that way, but if we decide as a class, okay, let's use rectangles to approximate this area. Tell me what you want students to go forward with. How do you want them to now approach all these examples?
Sure. So, as Brittany said, maybe using a rectangle, maybe using one rectangle gives you a real rough approximation of the area. It's probably not even close to the true area. So from there we say, well, what happens if we use two rectangles? Well, it's easy enough to find the area. You add the area of the one rectangle plus the area of the second rectangle, but it's still probably not a good approximation of the area. So I continue to have this conversation. What happens if we use 3 rectangles, 4 rectangles, 5, 10, 100? I don't go through all these examples with the students, but I just rhetorically ask them. And then from here, hopefully the students start to see, well, this kind of feels like the limit process. So maybe we're either taking the width of these rectangles, shrinking them down to 0, or maybe we're adding infinitely many rectangles. So this ties back in nicely into the previous section where we talked about sequences.
Yeah, and I think this is this perfect place, I think. I'm going to say that what we're trying to do here from a teacher's perspective is we're trying to lead the students with what I'll call a cliffhanger. And I say that because if we do this right, if we structure not only this section correctly, but this whole chapter, I think what we do is we try and ignite their interest in calculus. And so if I could leave them at the end of this chapter wanting more, I think that really is going to inspire some, at least, to go on further and ask some of these questions and seek the answers to them as well. I hope these tips have been helpful for you, and that you find much success in section 11.5.